When we consider crystals that are formed of neutral atoms, what holds them together is called the covalent bond. It's a strong bond formed between two neutral atoms. If you compare the cohesive energy for covalent bond and ionic bond, they are quite similar. The cohesive energy per atom is about 7 eV. It was 7 to 8 eV for ionic bond, so it's comparable to the ionic bonds. It has very strong directional properties due to hybridization. We will see that soon. The electrons forming the bond are partly localized in the region between the atoms. So these valence electrons are shared in such a way that the electrons overall fulfill the requirement of a closed shell, and when they occupy the same orbital, obviously they have to have opposite spins due to Pauli exclusion principle. So elements like silicon, germanium, carbon, etc. will form covalent bonds. Now, as an example, let's consider the hydrogen 2 plus ion. We have two protons and we have one electron that's going to be shared. The distance between two protons is a, and the electron has a relative position vector r1 with respect to the first proton and r2 with respect to the second nucleus. The potential energy of the system is q square over a minus q square over r1 minus q square over r2, where q is the electron charge because the proton and electron have the same charge with opposite signs. This equation is written in CGS units. Now, when the electron is close to either proton, it behaves as a hydrogenic 1s orbital. So we can expect that the molecular orbital for the H2 plus will be a linear combination of the two 1s orbitals centered at the two protons. So there are two possibilities. We can have a symmetric combination of the two orbitals, or we can have an anti-symmetric combination of the two orbitals. And when we look at absolute squared of the wave function psi, we obtain the charge distribution or the probability of finding the electron in a certain region in space. So when we have a symmetric combination of the atomic orbitals, that would be an anti-symmetric spin situation if it's occupied by two electrons, then you would see that there is a quite appreciable probability of finding the electron in between the two protons, two nuclei. On the other hand, if we have the anti-symmetric combination of atomic orbitals, we have in this case symmetric spins, then the psi squared gives us zero probability of finding the electron right in between the two protons. So we have the so-called bonding and anti-bonding orbitals. So what we're doing here is called linear combination of atomic orbitals to find the possible states the electron in between the two nuclei can occupy. Okay, so the two molecular orbitals, on the other hand, will have two different energies. So you can see that the symmetric combination will give you this Lennard-Jones potential. However, the anti-symmetric combination will give you a higher energy. So therefore, we find that it's preferable for the electron to contribute to the bond. So it should be in the symmetric combination. And the energy of the symmetric combination is negative, anti-symmetric combination is positive. Therefore, the symmetric combination gives us the stable state, and it's known as the bonding orbital, and that gives us an appreciable probability of finding the electron in between the two nuclei. For the anti-symmetric state, we have the anti-bonding orbital. That is when the electron is not in between the two nuclei. Now, these concepts can be applied to the hydrogen molecule with two electrons with opposite spins, and spin-dependent Coulomb energy due to the Pauli exclusion is called the exchange interaction. It's minus 4.48 eV for the hydrogen molecule. Okay, now if you look at carbon to show the directional properties of this bond, in carbon we have four valence electrons, 1s2, that's the filled core, 2s2 and 2p2. Now it will form, with covalent bonding, it will form bonds to 4 other carbon atoms so that each carbon will be surrounded by 8 valence electrons. So you can see that each carbon atom, so this is the carbon atom at the center, bonds to 4 other carbon atoms, and it provides 4 electrons and also uses 1 valence electron from each carbon atom to obtain a full shell, which is stable. So this situation, the covalent bonding that we see here, does not explain why we have a regular tetrahedron with a very specific angle 110 degrees between bonds. To understand this, the root of this angle and this tetrahedron shape, the directional property of the bond, we need to look at the spatial distribution of the valence electron orbitals. So in carbon, 1s2, 2s2, 2p2, S states are spherically symmetric and the p states represent charge distributions lying along 2 of the 3 Cartesian coordinates, so px, py, etc. So in carbon, one of the 2s electrons is excited into a p state, so that instead of 2s2, 2p2, we obtain 2s1, 2p3. The energy difference between 2s and 2p is small. So when we form linear combination of atomic orbitals, we have 1 over 2 s plus px plus py plus pz, s plus px plus py minus pz, s plus px minus py minus pz, s minus px minus py minus pz, parentheses 1/2. And if we plot these, psi 1 squared, psi 2 squared, psi 3 squared, psi 4 squared, these 4 atomic orbitals, we find that they distribute along tetrahedral direction. So here is what's happening. So we have the 2s orbital that's hybridizing with 3 2p orbitals, and that's forming 4 sp3 hybridized orbitals. And as you can see here, the center carbon atom is here, forming 4 covalent bonds to neighboring carbon atoms, and due to the sp3 bonding scheme, we have here about 110 degrees between bonds, and the electrons are residing in sp3 hybridized orbitals. So these types of orbitals give a maximum degree of overlap, so they give good chemical stability. The mixing of these S and P states is known as hybridization. In carbon, we have 2s and 2p states getting hybridized. In silicon, 3s, 3p. In germanium, 4s, 4p. So, however, we need to note that when we look at a crystal, we cannot say it's purely ionic bond or purely covalent bond. There is usually a mix of the two characters. So it would be better to say that we have some portion of the bond behaving as ionic and some portion as covalent. Okay, so to summarize, we talked about covalent bonding that is formed between neutral atoms which has directional properties. It is a bond that forms between atoms due to sharing of valence electrons that ends up fulfilling the requirement of the closed shell. We have seen that these atomic orbitals can form the symmetric or anti-symmetric combinations depending on the spins, and the symmetric combinations leads to bonding orbitals which has the lower energy, so that's the more stable one. And this spin dependent Coulomb energy, so whether we have a symmetric or anti-symmetric combination depending on the spin, is called the exchange interaction. And we have shown in the case of carbon with 4 valence electrons, we form 2s and 2p states hybridizing to form 2s1, 2p3 electrons are residing in sp3 hybridized orbitals, and the shape of these orbitals basically dictate this tetrahedron shape that has a 110 degree approximately a bond angle. And this hybridization is quite common. In silicon we have 3s, 3p. In germanium we have 4s and 4p getting hybridized. But in general, when we look at a crystal structure, we should consider the fact that there could be some ionic and some covalent character in the bond. So it's a mixed bonding character.